You know that smartphone in your hand? Yeah, it's a camera, a computer, a navigator, but what if I told you that inside it's this hidden city of almost unimaginable complexity? Come on, let's go explore that world together.
All right, let's just start with a number that sounds, well, completely impossible. Get this, the smartphone you're probably holding right now, it has over 110 meters of wires packed inside of it. No, seriously.
And to put that into perspective for you, that is about the length of a football field, an entire football field's worth of wiring, somehow comfortably packed into something that fits right in your pocket. How is that even possible?
Which, leads to the most obvious question. So, where on earth are they all hiding?
Well, the answer is this pretty remarkable piece of engineering, the printed circuit board, or PCB for short. This little thing? It's really the unsung hero of all modern electronics.
So let's dive in. What exactly is this electronic labyrinth? What does a printed circuit board actually do?
Okay, so a printed circuit board is basically a multi-layered board made of copper wires and insulation. And its job is kind of twofold. First, it provides the physical structure for all the components, and second, it allows every single one of them to communicate with each other totally seamlessly.
Now I know what you're thinking. You've probably heard the term motherboard, right? And it's super easy to get them confused. So think of it like this. A PCB is just the bare, flat board. A motherboard, on the other hand, is a PCB that already has all the components, like microchips and resistors, mounted onto it. So the PCB is the foundation, and the motherboard is the fully populated city built on top.
But okay, to actually see that football field's worth of wires, we have to look deep inside the board itself. And for that, we're going to need an X-ray.
And check this out. This is what the X-ray shows us. See those dark areas? Those are the conductive wires. Engineers call them traces, and they're made of copper. And all the lighter areas? That's the non-conductive insulator. It's a special fiberglass material called FR4, and its whole job is to keep all those thousands of signals from crossing paths and shorting out. Pretty cool.
But hold on, because here's where it gets truly amazing. A smartphone PCB isn't just one flat layer of wires. Nope. It's more like a 10-layer sandwich of pure technology. So let's break this tech sandwich down. You've got your top and bottom layers, right? That's for mounting components and for the antenna. Then you have these entire layers called power planes that are dedicated solely to distributing clean, stable electricity. Right next to those, you'll find ground planes for grounding, shielding, and helping to get rid of heat. And then, smack in the middle, are the signal layers. That's where all the real communication happens. And finally, the whole shebang is coated in a protective solder mask to keep it safe.
Okay, but that raises a pretty big question, doesn't it? If you have 10 separate conductive layers and they're all insulated from each other, how in the world do signals travel from one to another?
Well, they travel through these awesome little things called vias. A via, and yeah, that stands for Vertical Interconnect Access, is essentially a tiny metal-plated elevator for electricity. It's just a drilled hole that connects two or more of those copper layers, and it lets a signal move up or down through the board, just like an elevator.
And it gets even cooler. Engineers use different types of these vias for different needs. Some go all the way through the board, from top to bottom. Others are completely hidden inside, just connecting the internal layers. The level of precision here, it's just incredible.
Okay, so we've got all these layers and all these tiny connections, but what does that actually look like up close? Well, this is where we get into the truly mind-blowing scale of it all.
So let's go back to that X-ray image from before, and let's zoom in, way, way in.
Our source material from Branch Education put it perfectly with this visual. They said, and I quote, "Here's a dime so that you can get a sense of scale for the size of these wires." Just look at that. Now, what you're looking at here isn't just one set of wires. No way. You are seeing multiple sets on totally separate layers, all running in different directions, crisscrossing within a space that is less than 1 millimeter wide. It is literally a multi-lane superhighway in a space thinner than your credit card. That's insane. And listen, this level of engineering in miniature, it didn't just happen overnight. This is the result of decades of just relentless evolution in electronics. And this evolution is just incredible to see. Back in the day, older designs used what were called through-hole components. They had these little legs that actually passed through holes in the board, and by today's standards, they were huge. But modern designs, they use surface mount devices, or SMDs. These are soldered directly onto the surface, which has allowed components to shrink and shrink and shrink, to the point where some of them are now smaller than a flip.
And to keep shrinking everything down, engineers are using some seriously clever strategies. Like they might split functions between a main motherboard and a smaller daughter board. And get this, in the newest phones, they're even stacking entire circuit boards right on top of each other, all just to save a few millimeters for a bigger battery or a better camera.
So when you bring it all together, you realize the PCB is doing 3 incredible jobs all at once. It's the skeleton, right? Providing the physical structure. It's the city grid, creating a neat, organized home for every single component. And maybe most importantly, it's the nervous system, connecting everything in that vast, connected dots labyrinth of wires.
And really, that's what's so beautiful about it. It's the conceptual simplicity, just connecting point A to point B, combined with the absolutely staggering structural complexity of doing it millions of times on a microscopic scale, that really makes our entire modern world possible.
And this incredible engineering, it's not in a lab somewhere, it's in our pockets, right now. Which makes you wonder, doesn't it? What will the electronics of tomorrow even look like?